We're going to move to group work pretty quickly here, but let me just remind you what we were sort of talking about. We were doing this matrix vector product stuff last class. But actually what I want you to do, and we sort of talked about some of this stuff with these exploration questions, and then we the homework for tomorrow is also like just some practicing with this stuff. But then I want to talk about homogeneous systems, which are really important, which is basically where you have all zeros on the right-hand side. And we can write it as AX equals 0. And what I want you to do is, it's going to ask you to sort of like solve. Actually, there's a thing down here where it says find the general. So AX equals B. Sorry, I'm scrolling like mad, but AX equals B was this system here that we saw from page 1, where I tell you I told you a solution. But it's the same system, it's the same coefficient system, but just zeros after the equal sign is the homogeneous version. So it's just all the same. And so I think, before you start answering these questions, what you might want to do is actually solve in general. And but one is supposed to be equals B and one's supposed to be equal to 0. So there's a way to do that, to solve two things simultaneously, so you don't have to redo the steps of the row reduction, because that can be a little bit annoying. Which is, you could do something like this. You could write. Stop the share. You could write. Forgot these already. 1, -1, 3, -1. 2, 1, 3. And that's augmented. I like to draw the vertical bar. I know the book doesn't do it, but -2, 6, -3. But you could also put a second augmented column if you want it, because it's the same steps of the row reduction. And then it gets annoying if you row reduce one with a certain column, a certain augmented column, and then you have to do it again for a different augmented column, because you have to do all the row reduction steps again, but then it's going to change the other column. So what I'm saying is, in general, if you had different things after the equal sign and you want to solve, it's nice to just augment with more columns and then solve it all at once. Of course, here it doesn't really matter because these are all zeros. So you're going to end up with this. So these are never going to change. But I'm just saying you might want to do this first if you're going to row reduce, just so you don't have to resolve it. Okay. So what I want you to do, is we're going to get into groups, and I'll pause the recording and then basically solve this, what's on the board or on the screen. And then you can start to try to answer these questions. Answer questions 6 through 10, try to do like kind of explicitly what I'm asking you to do, like try to read what I'm asking you to do and do them. And then there's this generalization on the next page, and like we'll come back together and make sure we talk about all that. But if you finish 6 through 10, you can start looking at the next page also and see if you can figure out some of this generalization stuff. But that's the main thing I want to do today, is like start just to talk about homogeneous systems and like general parameterization of solution sets. Okay, fair? Do you want to be in the same groups we were in last time? Is that fine? Or do you guys remember what groups you were in last week? No? Didn't I just sort of like put you guys by group, by like where you sat in the class? Okay, so so just try to find the people. If you can remember what board you were at, just try to go to the board and find the people you worked with before. You guys can figure it out. I don't need to organize you that carefully, right? You're smart. Yeah, so go do this. So just do this first. That's kind of the tedious thing, actually row reducing, and maybe get all the way down to reduced echelon form, and then write the general solutions down. Oh, you guys are on the board. Oh, did I pause the recording? Let me pause the recording. Recording. All right, so we were talking about, so you guys have been you solved the system. There's 2 different systems that you solved, and I asked you to look at some of these questions on here, right, about what happens when you combine some of these different solutions. So let's maybe just sum up quickly. I'll just do this on the board. So your guys' work up here for a while. So this row reduced, right, as we said. And by the way, now I think maybe this might be the last time I try to really make you guys row reduce by hand. Once you're used to it, although you weren't all going down to fully reduced echelon form, I think that's the best thing to do. But you can just start to ask a computer to do it for you once you understand the algorithm, because it gets really tedious. And it's really more like, what can we conclude from the row reduction rather than like actually doing the steps of the row reduction, right? But if you row reduce, the third column ended up being free, right? And so that's a full row reduction. And then if you had the -2, 6, -3 after the equal sign, you get this. And if you have the 0, 0, 0 after the equal signs, obviously you're still with 0, 0, 0. And so, so this is kind of maybe, this is A, well, no, this was A. And this was B, and this was 0, right? So if we wanted to solve AX equals B, so what you can interpret these equations as is x1 plus 3x3 equals 7, x2 plus 7/3 x3 equals 14/3, and x4 equals -1. And then you can sort of solve. So when I talked about, and I guess x3 is free, maybe I should say. Well, okay, yeah, just x4 equals -1. So we're going to start writing things like this. So if I actually solved this and put everything in terms of the free variable, this would be 7 minus 3x3. This would be 14/3 minus 7/3 x3. Is it clear that x3 is not in the denominator? Still maybe not clear. And then x3 is just x3, and x4 is forced to be -1, right? So that could be like a general solution to AX equals B. General solution. And if you do AX equals 0, it's pretty similar, right? You get x1 plus 3x3 equals 0. x2 plus 7/3 x3 equals 0. And x4 equals 0. And so now the general solution is, maybe I'm tempted to call it like U1, U2, U3, U4 or something, but because I was using the letter U up there on the screen. But now the general solution is just -3x3, -7/3 x3, x3, and 0, right? So that's what I meant by sort of the general solutions. And then when you explored what happens, like, so you can make two different, right? You can make two different homogeneous solutions by just picking different values of x3, right? And so what you found was that all these combinations also were solutions of AX equals 0, right? That's what you guys found. I think most of the groups, all the groups found that. So exploration. So if U1 and U2, and again, this is called the homogeneous system. This is called homogeneous. So if U1 and U2 are homogeneous solutions, meaning they satisfy AX equals 0. Then so is U1 plus U2, U1 minus U2, 2U1, any combination. 2U1 plus 3U2, et cetera. Right? So that was the first thing you found. And then the second thing was like, if x naught solves ax equals b, and u solves ax equals 0, that was what number, like 9 or 10 or whatever it was asking. Then, yeah, and there's a name for these, by the way. So, like I said, this is called, I mean, if you have a system, you might start with a system like this. And I guess my point I'm going to make is that it's always helpful to think about the associated homogeneous system. It's sort of nice to just make the thing after the equal sign 0, because they're going to be related. And so this is called a particular solution, like in textbooks and stuff. And this is called a homogeneous solution. I guess in other disciplines, you pronounce that homogeneous, but mathematicians for some reason say homogeneous. I don't know why. Like heterogeneous when we say heterogeneous. Yeah, so that's what those are called. And if you had x naught solving, dropping some of my vectors, solving that and u solving that, I know you guys had it over here, right? That if you did both, if you added them, if you added two of these solutions, I think you actually got another solution to ax equals b. So, and you guys had that too. I see Zephyr nodding. Then x naught plus u is solves ax equals b. By solves, I just mean is a solution of. It's my shorthand way of writing. Or it's another particular solution. Yeah. Little a and little b, not. Well, that's interesting. Yeah.
So wait,
I'll go to.
The ax vector at the bottom, that equals x naught plus u. That little x in the ax vector.
Oh yeah, I'm saying if you actually do a times quantity x naught plus u,
Yeah.
you will get b. Yeah, and then for your, okay, so now, yeah, so think about it. So like, there was this other question, I think back to Zephyr's, what about x naught plus x naught? Did that work as a solution? You guys said no, right? Because if you plug it in, I mean, it's sort of interesting to try to see this, but like, we can sort of see why. And we'll talk about generally why this is happening, but maybe we should do it for this specific. I'm gonna erase your beautiful work, I'm sorry. All right. Yeah, but that's a good question. So what happens if you try x naught plus x naught? So like, let's just do it together. I don't think most of the groups got to it. So what about x naught plus x naught? So x naught was, what was it, 1, 0, 2, negative 1? No. Yes. Yeah, you can actually see it here too. If you plug in x3 is 2, you can recover that specific solution we had on page 1 of the handout. If x3 is 2, then you get 7 minus 6, which is 1. And you get 14/3 minus 14/3, which is 0. So x naught is 1, 0, 2, negative 1. This really came from picking x3 equals 2. Then x naught plus x naught, you guys have it over there, it's 2, 0, 4, negative 2. Let's compute a times x naught. So let me just write the same. I'm just going to do some matrix multiplication instead of plugging in. I mean, it's the same thing. when it comes down to it. 2, 1, 3. So what happens when we multiply this? Did you guys see what you got? I guess, oh, did you just try the first one and saw it didn't work? Or did you try them all? I can see there's something not equal down there on the bottom right, but if you actually multiply this through, let's see. So you get 2 times 2 is 4, plus 0, minus 4 is 0, minus 4 is -4. I'm doing that dot product thing. I'm a professional, so I've gotten good at this. 2 plus 12 is 14, minus 2 is 12. 4 minus 4 is 0, minus 6 is -6. So that's not B, right? What was B? -2, 6, -3. But there should be something that jumps out at you. What is it? It's twice B. That's interesting. That's B. That's twice B. So it's not a solution. It's definitely not a solution of AX equals B. But it does give you twice B, which is interesting. And I think Edie actually wrote what's going on here. So there's actually nice explanations for all of this, which is that here's the important point. Matrix multiplication distributes over addition. A times x1 plus x2, if these are two different vectors, is the same, or maybe I'll just use, well, that's fine, x1, x2, is ax1 plus ax2. You can check that. It's not that hard to check. But it really does, it is distributive. So like, yeah, you can see it. Just for example, if I had like, I don't know, if I had a matrix made up of 2 vectors and I wanted to multiply it by like, yeah, just, I used X's already. Let's just say A1, B1, A1 plus B1, A2 plus B2. By definition, one way we thought about this is we thought about these as weights on the columns of the matrix, right? So that's just this times the first column, this times the second column. These are scalars, right? This is supposed to be like the x1 plus x2. Yeah, sorry, x1 is A1, A2. And x2 here. My numbering system's kind of bad because I've got 1s and 2s floating around here, confusing away. But, and then what's clear is you can just rearrange this, right? You can rearrange this as, because this is distributive. So you can rearrange this as like A1, V1 plus A2, V2 plus B1, V1 plus B2, V2. This is supposed to be A times x1 plus x2. But this is clearly A times x1, right? Because, or maybe I can just say we can factor that as column V1, column V2 times vector A1, A2 plus column V1, column V2 times vector B1, B2. And that's AX1. AX1 plus AX2. So you can sort of check that this is, I mean, that's one thing that's really nice about linear things. That's why actually linear algebra is so useful, is because it really comes down to distributing, like the distributive law. Like a lot of things we're going to do is just going to be like distribute, rearrange. And it's like not that deep, but you can kind of do it over and over again. So this is important because I think this answers all of this stuff, like why Like, can you see now why like combinations of U1 and U2 are also homogeneous solutions? If you think about just a solution is something that when you multiply by A, you get 0. Again, I erased it, but I know Edie and I were talking about it. Yeah, so let me just let me leave these up here for a minute. This justifies all of these things, and that's what the next page of the handout actually is this like, it's this sort of general thing. So like, yeah, I can think about this very generically, but I was just trying to use this to use this example to illustrate all this stuff. So, oh, by the way, it also like matrix multiplication respects addition. That's another way mathematicians will say it, like that it distributes over addition. It also respects scaling. You could say that a times a scaled vector is the scalar times this vector, right? Like the scalar kind of pulls out. You can check that too. And yeah, so this actually, this explains all these conclusions. This explains all these patterns. Right, if, for example, if U1 and U2 satisfy AX equals 0, right, then what happens when you do U1 plus U2? Oh, I've erased the particular solution. That's unfortunate. Right, what happens now when I try to plug in U1 plus U2? What do I want to write next? What does A times U1 plus U2 equal? Well, no. Well, what does it equal just based on what we said up there? Right? It's just AU1 plus AU2. And what does AU1 equal? 0, because it satisfies this. So that's 0 plus 0, which is 0. So that's why, like, when you add two homogeneous solutions, you get another homogeneous solution. And you can, and it works out, you can sort of tell it works out for all like linear combinations. But then also, if X naught satisfies AX equals B, and U, or U1, satisfies AX equals 0, then when you try to do A times X naught plus U1, right, you guys see what's happening now? Just distribute and plug in, right? Is that working? Zephyr's making a face. Okay. It's hard to tell with the masks, but right, that's just that. Or AX naught, sorry. But AX naught equals B and AU1 equals 0. So that's B plus 0 equals B. Okay, so the idea is that, oh, and even you guys even got to like, if you have two particular solutions, V1 and V2, then what about the difference? What was the difference? Homogeneous solution, yeah. And so also if V1, V2 satisfy AX equals B, then think about V1 minus V2. Then A times V1 minus V2 is AV1 minus AV2, which is B minus B, which is 0. So V1 minus V2 is a homogeneous solution. So in particular, we can say three things here. We can say homogeneous or linear combinations of homogeneous solutions are homogeneous. We can say if we take a particular solution and add a homogeneous solution, we get another particular solution. We could say if we subtract two particular solutions, then we get a homogeneous solution. So there's a whole structure here that's sort of interesting, right? So the conclusion homogeneous plus homogeneous. I'm gonna get lazy and write homog. And then two particular plus homogeneous equals another particular. I mean, these aren't really equations. I'm just saying, like, these are more like statements, right? And then the three was that particular minus particular is homogeneous. And there's really interesting reasons sort of why. I mean, I don't think we'll do it today, but next time I'll show you some geometric ways to interpret this. Okay, cool. Okay, just to actually maybe just, yeah, you can sort of say here, I mean, if you read down this page, whatever, page 3 of this handout, you can make this more mathematically formal and basically saying the set of all solutions to a system of equations is the set of homogeneous solutions plus one particular solution. So let me actually notice that with that example that we had. I think it's probably the best thing to do. So I erased it already, but when we wrote, yeah, I do want to get this done before. When we wrote this, AX equals B, what was the solution that we had? Someone remind me of what I wrote down. I erased it. I know we had x3 and -1, right? What do we have? Should be in your notes. Seven minus 3x3 and 14/3. Oh, right. I'm going to do something. I'm going to rewrite this. I'm going to rewrite this in the following way. I can think of this as 0 plus 1x3. And I can think of this as -1 plus 0 x3s. Right? I want to just be a little more formal. And then I can break this up as 7 14/3 0 minus 1 plus -3x3 -7/3 x3 x3 0. This is a particular solution right here. You could check that this actually satisfies the system. And this is all the homogeneous solutions, right? You sort of found that. That's actually, if you look at the homogeneous solutions, that's exactly what we had, right? You just drop the constants. And so that illustrates that basically all solutions are, you just need to find a particular solution and then find the homogeneous solutions, and that's what you get, yeah. You could change this to that one we gave. It would just kind of shift all the solutions in a weird way, but it would still give all possible solutions. Yeah, but let me just write one more thing. So the way that we'll tend to present solutions to systems is like this. We're actually going to take this x3 and factor it out. And write it like that. And it's basically the free variable becomes like a scalar. And if there are more free variables, you could break it up more. But this is like a particular solution. This is still particular. And this is like a special homogeneous solution, right? I think when you set the free variable equal to 1, you guys got this for the homogeneous solution, right? So this is a special homogeneous solution. And so all solutions equals, if I just write x1, x2, x3, x4, this is all solutions. And so this is called like a parametric form of solutions, where you're basically the free variables become the parameters. Parametric vector form, actually, it's called. Parametric vector form. Just want to make sure I get to that because it's going to be on the homework for Tuesday. That this is what's called the parametric vector form of the solutions right here. Okay, that like, it's just a nice way to write down a set of solutions to a system of linear equations, because you're basically seeing all the structure. You're seeing a particular solution, you're seeing the homogeneous solutions, you're seeing the free variables as these like scalars in front of the, and these are, you think of these as vectors. Does that all make sense? Yeah. Oh, sorry. Cut things off. Yeah, and so this is a general fact that basically all solutions, like if you solve any system, I mean, we had the augmented zero column, and all it did, you know, when we had a non-zero column, all it did to change the solution was put some non-zero numbers in the constants in the solution, right? And so there's this idea that the homogeneous system is kind of like the base system, and then if you make the stuff after the equal sign non-zero, then you get these different solutions that are, I'll show you geometrically, they all kind of in a parallel, like this is, this right here is some line in 4-dimensional space. So the solutions are actually a subspace. They're actually a line through the origin. Because 0, 0, 0, 0 is always the solution of a homogeneous system. And what this does is this just moves it off that line. It just shifts this line away from the origin. I'll show you an example on Tuesday, but it's kind of interesting how like, there's some, you'll see pictures like this. You'll see pictures like, yeah, you'll see pictures like, like that, and this is like homogeneous solutions. To AX, you know, AX equals 0, solutions to AX equals 0. And then you'll see a parallel line here. Because if you think about it, this is like a particular vector. So it's like going from the origin out to a particular vector. It's kind of like how we parameterize lines, if you remember in 1800, if you took multi here, which is like, you go off the origin to the line and then you follow the line. And so this is like your particular solution. And then this, but then this line is all solutions to, say here, like all solutions to AX equals B. And here we only had one free variable, so that's a 1-dimensional space of solutions. If we had 2 free variables, you could have like a plane of solutions to the origin as a homogeneous, and then like a parallel plane of like solutions to like the general system. Okay. Just kind of some of the weird geometry of this. I'll show you, like I said, on class next Tuesday, I'll do some smaller dimensional examples where we can actually really see it. And then we'll move on to other stuff. Should we call it a day? It's a little early, but yeah, please erase your boards if you could help me out. And make sure the chairs are straightened up. And I don't know who left their drink up here. So the problem set for tomorrow was stuff from Tuesday, the matrix vector stuff. It's pretty simple. I don't think it's that hard. And then I'll post stuff about this for homework for Tuesday night. Oh, let me stop. Did I even resume recording? Let me stop recording. I did.